In this lecture, we will be discussing the unusual oxidation states of the actinide ions. Uranium 5 species we have reported before while studying the aqueous ionic species of actinides. Now U5, that is UO2 plus ion, has a very low stability in the aqueous medium, but some of the uranium 5 complexes given in this scheme, you can see these type of complexes, they are stable for even 7 to 10 days. In pH 7 to 10 for several days, these type of complexes are stable. And the medium where these type of complexes are formed is DMSO, THF or pyridine. In all these cases, this 222 krypton plays a very important role while forming this type of complexes, because that forms a cationic species with the potassium, and then this complex which is having an anionic species are mentioned here. This forms sort of an ion pair, and that is how it is stable. Plutonium 7 and Neptunium 7 are already reported in solids or solution phases in alkaline media. Some of the examples are given here. This type of species which is mentioned are there. Now plutonyl nitrate complex, which is reported whether plutonium is heptavalent in the PuO3NO3 2-, this type of species, the structure which is given below. So here it has been proven theoretically that plutonium may be heptavalent in this type of complexes. Now unusual oxidation state of thorium. As we know, thorium has +4 as the most common oxidation state, and because of the F0 configuration, it has very stable oxidation state, and we have most of the thorium complexes in the +4 states. But there are some reports in which in thorium 3 complex, this is the tris cyclopentadienyl thorium, this complex is reported, where thorium is in the +3 oxidation state, and also analogous complex is also formed, and where thorium is having +2 as the oxidation state. So these are some of the unusual oxidation states of thorium. There are many other examples, but I have quoted only these two here. And also there is an interesting species of thorium 3+ in the C80 fullerene structure as given here. In this case, you have two thorium 3+ ions going inside the fullerene case, and they are getting stabilized due to the thorium pi interaction within the fullerene system as shown here. Very stable complex formation is there, where the thorium to thorium bond distance is around 3.816 angstrom as shown here. And this has been proven both by experimental as well as quantum chemical studies. Americium 4, as I have already mentioned in previous classes, the most stable oxidation state of americium in aqueous solutions is the +3 state. Now americium 4 formation is very difficult because immediately it disproportionates as shown here, the low acid concentration. So 3 americium 4+ plus 2 H2O going to 2 americium 3+ plus AmO2 2+ species. Now this americium 4 species, this has disproportionated, and this diagram is given here, where the starting concentration of americium is 10 to the power or -3 molar, that is a millimolar solution of americium 4 has been taken, and that is disproportionating. You can see here with the americium 6 and americium 3. The concentration of americium 3 is roughly twice that of americium 6, which is satisfying the equation given above. The profiles of americium species are presented in the figure given here. Americium 6, I have mentioned before that it is used in the session process for the separation of americium and curium. So americium 3 is oxidized to americium 6 or AmO2 2 plus ion by ammonium persulfate, and then PVP extraction of americium 6 can be done in the similar manner as the uranyl ion extraction is done from the nitric acid medium. Now coming to the analytical chemistry of actinides, we should be in a position to analyze the actinides. Those of them are highly radioactive, then there is not a problem because we can go for the radiometric method of estimation. But those with relatively lower radioactivity, there are other methods for analysis. So I will be giving a general method of analysis for some of the early actinides like thorium, uranium, neptunium and plutonium. These 4 actinides I will be mostly discussing. And these actinides, they form insoluble precipitates in their +4 oxidation state with hydroxide, oxalate, iodate, fluoride or even peroxide. It can also be done by organic reagents such as copperon, benzoic acid or hydroxyquinoline, and those precipitates can be filtered and estimated by gravimetric method. For thorium +4, the inorganic precipitates, as I have already mentioned, such as the thorium hydroxide or peroxide or oxalates, they can be heated in a furnace to yield the oxide, that is THO2, and the organic precipitates, they can be directly filtered, dried and weighed to give the exact amount of thorium. There may be interference if there are other tetravalent ions present in the solution like zirconium, titanium, hafnium or even some trivalent metal ions like the rare earth element. Uranium precipitation can be done by carbonate-free ammonia to yield ADU or ammonium diuranate, which can be converted to U3O8 upon heating, and then by weighing this we can find out how much is the uranium present in this final product. Neptunium, in this case, in the +4 oxidation state, can be precipitated as oxalate or peroxide from hydrochloric acid or nitric acid medium. Same way, plutonium 4 plus can be precipitated as its insoluble peroxide, hydroxide or oxalate. Plutonium valency adjustment is required in this case, as I have already mentioned. This nitrite ion can be used for the oxidation of plutonium 3 plus to plutonium 4 plus or the reduction of PuO2 2 plus to Pu4 plus ion. The other popular method of analysis of the early actinides like thorium, uranium, neptunium and plutonium is spectrophotometry. For thorium, very specific reagent is there, that is thoron, which can be used to obtain the red colored complex of thorium 4 plus with a lambda max at 545 nanometer. However, there can be interference from zirconium, titanium or other tetravalent actinides. Arsenazo 3 is also used for the estimation of thorium 4 plus, where it observes at 650 nanometer, but there can be serious interference by other actinides like uranium and plutonium, which also form complexes giving rise to color and observing at again close to 650 nanometer. Uranium can be analyzed spectrophotometrically by different methods. Uranium itself, it observes in the range of 400 to 450 nanometer. That means the yellow colored uranyl nitrate solution, it can be used for its estimation with a epsilon value of around 30, and around 1 milligram per ml solution is used for this purpose. If the concentration is less than 1 milligram per ml, then we go for other more sensitive methods like the thiocyanate complex formation is done of uranyl ion, which gives an intense yellow colored solution with a lambda max at around 375 nanometer with epsilon value of 3850. So that means nearly 2 orders of magnitude as compared to the only uranyl nitrate solution. But the interference with thiocyanate can be there from the transition metals, like the iron thiocyanate complex also forms intense red color, and it can interfere with the uranium estimation. Dibenzoyl methane or DBM, this forms a complex with the uranyl ion with a lambda max value at 417 nanometer with a epsilon value again very close to this thiocyanate complex, that is 3850. Bromopetak, it's another ligand which is used for complex formation with the uranyl ion. It has a lambda max value of 575 nanometer with epsilon value of 74,000. So it's a very high absorption is there, and with a very low concentration of uranium can be estimated by this method. Neptunium 4 can be estimated if it is there in the nitric acid solution at 964 and 704 nanometer. These are the characteristic bands of Neptunium 4 with epsilon value close to 100. Neptunium 5, it has a sharp band at 983 nanometer, and Neptunium 6 has again a sharp band at 1230 nanometer. Arsenazole 3 forms a green colored complex with Neptunium 4 in hydrochloric acid or the nitric acid medium with a lambda max at around 665 nanometer. But quantitative reduction has to be ensured, otherwise there will be errors in the results. So Neptunium oxidation state has to be maintained at +4 by using reagents like ferrous sulfamate, which we have already discussed. Neptunium 4 also forms color complex with thoron with lambda max at around 540 nanometer. So it can interfere with the estimation of thorium, and the same way thorium also can interfere with an estimation of neptunium by thoron. Plutonium species give characteristic absorption bands. Plutonium 3 has characteristic bands at 603 and 560 nanometer. Plutonium 4 at 470 and 700 nanometer, and plutonium 6 at 953 and 833 nanometer. Thoron and arsenazole 3 can also be used for the estimation of plutonium 4 plus ion, but the results can be erroneous if some of the actinide ions like thorium 4 plus or neptunium 4 plus is present in the solution. Now coming to another important topic is the autoradiolysis. We know most of the actinides, they are undergoing alpha decay, and under the action of its own alpha radiation, the actinides can undergo oxidation and reduction reactions. So I have taken in this case only the case of plutonium, which is one of the most important actinides, and plutonium oxidation state, how it is changing because of this radiation emitting from the plutonium. I will be discussing that in this section. So because of this alpha radiation, plutonium 6 is reduced to plutonium 5, which in turn disproportionates. Plutonium 4, which is formed from the disproportionation reaction, and it reacts with the plutonium 5 again to give the plutonium 3 and plutonium 6. So that is how plutonium 6, if it is present under the autoradiolysis, it can go to the all the 4 oxidation states like 6, 5, 4 and 3, and after some time we have the mixture of plutonium 6, 4 and 3 because 5 is immediately disproportionate. Now plutonium mostly consists of the 2 alpha emitting nuclides, that is 238 plutonium, 239 plutonium with half-lives of 88 years and 2.4 into 10 to the power 4 years. But other plutonium isotopes are also giving alpha, but these two are the most important. So that is why I am considering these 2 isotopes of plutonium. And the alpha which is emitting from them, you can see if you have 1 milligram of plutonium 238, this gives 4 into 10 to the power 10 alpha per minute. And if you have 1 milligram of plutonium 239, it gives 1.4 into 10 to the power 8 alpha per minute. So because of this intense alpha radiation, there is going to be radiolysis of water, which forms species like hydrogen peroxide and also species like hydrated electron, OH radical, H radical, O minus radical, and also O2H, which also gives different products which can oxidize or reduce the plutonium ions. Also, the decomposition products of the acids in which the plutonium solution is made, like whether it is a hydrochloric acid, perchloric acid, or nitric acid, those radiolytic degradation products of the acids also will be playing a part in the redox chemistry of plutonium in this medium. So reduction of plutonium 6 in 0.2 molar perchloric acid under the action of the alpha particles which are emitted by 210 polonium. This has been taken because more number of alpha particles are emitted from 210 polonium, and this can be used as an intense alpha source. So when this, in this study, when this radiation dose is lower than 3 kilogray, then plutonium 5 forms in the solution with a G value of 3.2. So the G value means with 100 eV radiation, how many products are formed, that is 3.2 is the average value formed. And when the dose is higher than 3 kilogray, then plutonium 4 is formed with a G value of 1.6. Finally, when the dose exceeds 11 kilogray, plutonium 3 is accumulated with a G value of 1.1. So these products which are formed from the radiolysis of plutonium 6 in the presence of 210 polonium, this does not depend whether this reaction is taking place in the presence of air or not. The theoretical yield for the reduction of plutonium 6 to 4 is 3 ions per 100 electron volt, which is in agreement with the experimental results obtained in this study as mentioned above. Continuing in this autoradiolysis, in a 1 molar solution of perchloric acid containing 0.01 molar plutonium 239 in the +4 oxidation state at 25 degrees, the average oxidation number of plutonium changes by 0.014 every day until it becomes 3.02 to 3.05. The gas evolved from this solution, which consists of oxygen and hydrogen, which is coming from the radiolysis of water. And also the solution is found to contain a substantial amount of chloride ion, which is coming from the radiolysis of perchloric acid. The theoretical reduction yield of plutonium 4, like that of the plutonium 6 just discussed in the previous slide, is around 3 ions per 100 electron volt. The G value of 3.5, which is experimentally seen, is because of the slightly error due to the plutonium 4 reduction from the radicals from the spores actually coming because of the alpha particles. The radiolytic transformations of 238 plutonium, which is giving significantly more number of alpha particles, again in the +4 oxidation state and in the +6 oxidation state, was studied in 1 molar perchloric acid, and the radiation dose was around 0.15 gray per second. The concentration of plutonium 4 remained constant in this case, whereas that of plutonium 6 was reduced to give plutonium 4 and plutonium 3. The yield in this case was low due to the slow reaction in 1 molar perchloric acid. Autoradiolysis of plutonium in nitric acid medium. Nitric acid medium also leads to the autoradiolysis of plutonium, similar way as I mentioned for the perchloric acid. In 0.18 molar nitric acid, if we have a solution of 0.01 to 0.03 molar plutonium, which contains around 80% 238 plutonium and 20% 239 plutonium, then it was found to have average oxidation state of 3.3. With increasing the nitric acid concentration to around 1 molar, the average oxidation state has changed to around 4. If 100% plutonium-6 was taken, then there is an induction period initially if the concentration of the nitric acid was less than 1 molar, and subsequently the plutonium-6 was found to be reduced to the +3 as well as +4 oxidation state. But in the presence of plutonium-3 and plutonium-4, there is no induction period. That is to say, if the plutonium-6 also contains some amount of plutonium-3 and plutonium-4 to start with, then there is no induction period and we have immediately these redox reactions taking place. What are the redox reactions? This plutonium-6 takes up 1 electron and gets reduced to plutonium-5. Same way, plutonium-5 gets reduced to plutonium-4, and plutonium-5 is disproportionating to plutonium-4 and plutonium-6, and again plutonium-4 is reduced to give plutonium-3. There is also a reproportionation reaction where plutonium-6 combines with a plutonium-3 to give plutonium-5 and plutonium-4, and also plutonium-5 reacts with plutonium-3 to give 2 ions of plutonium-4 plus. At higher nitric acid concentration, plutonium-4 is getting converted to plutonium-6. For a 10 millimolar solution of plutonium in 6 molar nitric acid, the dose rate of 1.4 watts per liter yielded a plutonium-6 to plutonium-4 ratio of 0.76, which significantly gets enhanced to around 3.15. That is, the ratio of plutonium-6 to plutonium-4 becomes 3.15 if the dose rate was increased to 13.8 watts per liter of the solution. Now coming to the applications of the actinides. One of the major applications of the actinides is in the nuclear energy, that is uranium-235, uranium-233 and plutonium-239. So these are the fissile isotopes of the actinides which are used in the nuclear energy. Also, the actinides are used as the power sources. That is to say, some of the actinide isotopes are the radionuclides like 227 actinium and 228 thorium, 238 plutonium, with 242 curium. They are used as power sources. 227 actinium, which has a specific power density of 2.127 watts per gram, but it has a limited use. It requires heavy shielding for its application as a power source. Similarly, thorium-228, which has a specific power density of 26.05 watts per gram. This also has a limited use and it also requires heavy shielding while applying it as a power source. 238 plutonium, this has a specific power density of 0.54 watts per gram. This has been used as a power source in space shuttles. 242 curium, which has a specific power density of 120 watts per gram. This has relatively short half-life of around 2.2 years or so. So it also has a very good use as a power source. There are some of the other applications of the actinides, like plutonium-238 is used as a pacemaker. Actinium-225 is used in the alpha therapy. As we know, these days for the cancer therapy, even though we are using previously other beta gamma emitting radionuclides, the alpha therapy or the alpha emitting radionuclides are finding a great application because of very specific way it destroys the tumor cells due to high linear energy transfer of the alpha particles. So in this way, actinium-225 is one of the very useful radionuclide used in the alpha therapy. Actinides are also used as neutron sources. There are examples where this americium, beryllium, which are used as neutron sources, giving 2 into 10 to the power 6 neutrons per curie of the radionuclide. There are also examples of plutonium beryllium source being used for the neutron generation. Californium 252, which is having a spontaneous fission, it gives neutrons from the spontaneous fission reaction, and it has this 4.4 into 10 to the power 9 neutrons per curie of the radionuclide. There are also applications of the actinides, like americium 241 is used in smoke detectors. Thorium is also used in gas metals. Now to summarize, the actinides as it is produced in the nuclear reactors, they also can be produced by heavy ion reactions in accelerators. In these actinides, they have a very interesting chemical properties. Apart from being used in the nuclear power industry, they also have several other uses. And as I mentioned, 238 plutonium is a very popular radionuclide as a power source. And when this neptunium 237, which is there in the radioactive waste, that is the high level liquid waste, there is proposal in different countries to separate the 237 neptunium radionuclide from the high level waste and irradiate in a reactor to get 238 plutonium, which can have used as a power source. Then also we have seen how these actinides have very, very interesting chemical properties because of their multiple oxidation states. Many cases, the unusual oxidation states like neptunium 5, plutonium 5, uranium 5, they get disproportionated under the given chemical condition to give other more stable oxidation states like the pentavalent and hexavalent states. That is how the chemistry of these actinides, depending on the aqueous medium in which these type of oxidation states are present, so that their chemistry can be studied. And mostly, as we have seen, the chemistry of actinides in the +4 as well as +6 oxidation states are important so far as the nuclear fuel reprocessing is concerned. And other actinides are present mostly in the +3 oxidation states like the transplutonium elements, and the minor actinide like neptunium, which also is present in the +4 as well as +6 oxidation states, can be separated by using several separation methods from the radioactive waste feeds. The use of the actinides also I have mentioned. That is how we come to the end of this actinide part of this lecture series. Now we'll be covering actinides in the environment and then the transactinides.